Hi everyone. So, in the last session, we were dealing with the nucleophilic substitution mechanism. Hope you have understood the SN1 and the SN2 mechanism, which is very, very important. Okay, and hope you have done that homework. And all the points, I think you are remembering that, all the value points, okay, of the SN1 and the SN2. That is substitution, nucleophilic, bimolecular, and substitution, nucleophilic, unimolecular. Now, before going into the details, we will see some of the stereochemical aspects of nucleophilic substitution. Now, what do you mean by stereochemical aspects? Stereochemical aspects means which is related to stereochemistry. Okay, stereochemistry means what? The arrangement, the spatial arrangement of molecules. Okay, the different type of spatial arrangements in the molecule, we call it as stereochemistry. Okay, so then you have to come across with certain terminologies. Okay, before going into the details of this substitution nucleophilic, we will see some of the terminologies which come across in the this stereochemistry. We will say stereochemistry. Okay. Now, some of the terminologies are, first we will see what do you mean by optical activity, or what do you mean by optically active compounds. Okay. So, first we will see what is optically active compounds. Okay. So, optical active compounds. Okay. And the compounds which shows this behavior or this phenomenon is said to be optically active isomeres, and the phenomenon is called as optical activity. Now, what is this optical activity? See, some compounds when passed through a plane polarized light. What do you mean by plane polarized light? Plane polarized light means a white light which is passed through a Nicol prism, we call it as a PPL, or a plane polarized light. So, some compounds, when it is passed through a PP or a plane polarized light, it will show two types of deviations. One is, it rotates this plane polarized light towards right, and second is, these compounds will rotate the plane polarized light towards the left. You got it? That means, if in some compounds, in certain organic compounds, when it is passed through a PPL or a plane polarized light, what happens? This has got the rotations. Okay, and some will rotate to the right hand side, whether some other will rotate to the left hand side. Okay, so the angle by which, how much angle it makes the rotation, that you can calculate or measure by means of an instrument called as polarimeter. When you go for a higher level chemistry, you will have this experiment to be done using the polarimeter. Okay, so that is called as polarimeter. Polarimeter. Okay, so the angle made by these compounds, how much angle, for example 32 degree towards the right or 15 degree towards the left, that angle you can measure it from an instrument called as polarimeter. Now, a compound which rotates the plane polarized light towards the right is called as dextrorotatory. What is it? Dextrorotatory. Dextro means right. Okay, and the compounds which rotate the PPL towards the left or in the opposite direction. If you say clockwise, for one, if we say clockwise, if you say it is dextro, then you can say for anti-clockwise, it is called as a levo. Okay. So here we will say the compounds which rotate the plane polarized light towards the right is called as dextro, and towards the left is called as levo. Okay. So towards the left is called as levo. So now you know what is dextrorotatory and levorotatory. Okay. The best examples, glucose. You know glucose and fructose. How glucose and fructose is formed? By the hydrolysis of sucrose, C12H22O11, isn't it? So, sucrose on hydrolysis will give you fructose and glucose. We have to study the biomolecules. There's a chapter called as biomolecules where it is beautifully illustrated how this glucose is dextrorotatory. That is, glucose is dextrorotatory. That means what? When the plain polarized light is passed through glucose solution, or the glucose solution is passed through that light, what happens? It rotates this PPL towards the right. That is called as dextrorotatory. So glucose is a dextrorotatory thing, whereas fructose, glucose and fructose have the same formula, C6H12O6, but fructose for that matter is levorotatory. What is levorotatory? This rotates the plane polarized light towards the left. So that is the difference between dextro and levo. And the compounds which shows this isomerism or this kind of rotational behavior is called as optically active compounds. We can say these compounds which rotate the plane polarized light either towards the right or towards the left is said to be optically active compounds, and the phenomenon is called as optical activity. Got it? Now what is optical activity? The phenomenon by which certain compounds rotate the PPL towards right or left. Towards the right means it is called as dextrorotatory, which simple. That's a simple for dextrorotatory. Even you can write plus or you can write D, small d. Very, very important. Why I said small d? Because there is one capital D also. Okay, the capital D is for the configuration. You will study later. So levorotatory or left you can designate by minus or L. Either one. Okay, either one you can designate. Either you put plus or minus, or you can put D and L. So this is about the optical isomerism. The compounds which show such type of rotation behavior is called as what? Dextrorotatory. Which is called as optical isomerism. And the compounds are called to be optically active compounds. And so for example, I said what glucose is dextrorotatory, whereas fructose is levorotatory. Then you can denote it by the symbol either by plus for dextro and minus for levo, or you can have small d for dextro and small l for levo. Clear? Okay. Now we will pass on to the second terminology, which is called as molecular asymmetry. You have studied in physics, isn't it? What about the symmetries? Line of symmetry, plane of symmetry, center of symmetry, etc. You have studied, I hope. This year you have studied. So here, in chemical point of view, what is called as molecular asymmetry? And in related to the molecular asymmetry, we will talk about what is chirality. Chirality, that is, when we say a molecule is chiral, or when we say a molecule is achiral, etc. Now you know what is molecular symmetry. When we talk about molecular symmetry, there are three kinds of symmetry, like plane of symmetry, center of symmetry, etc. Point of symmetry, etc. So when Louis Pasteur was examining this symmetry, he came to observe that these compounds which shows symmetry is not optically active. Got it? He made researches. Louis Pasteur, you know him, right? Louis Pasteur. When he was examining these organic compounds of these optically active compounds, he noted that the compounds which show optical isomerism did not have a molecular symmetry, or it will be a molecular asymmetric compounds. Or in other words, I can say molecular asymmetric compounds will show optical isomerism. That was the conclusion of his observations. Which means if a compound is said to be optically active means what? It has to rotate the PPL either towards the right or towards the left. If that should happen, then the molecule must be molecular, or it should have molecular asymmetry. What is it? Asymmetry. Okay. So it will have molecular asymmetry. If it is having a symmetry, then it won't show the optical activity or optical isomerism. Correct. Now when we will say a a molecule is asymmetric, or when we will say a molecule is of symmetric type. There you will come across with another word which is called as chilarity or chiral. Chilarity or chiral. Okay. Now what is this? What do you mean by chiral? For example, you have considered a compound. You are having a compound. Carbon, you know the valency of carbon is 4, and if the four valency of carbon atom are satisfied by 4 different groups, A, B, C is there, so B and E. See, A, B, C, D and E. Then this carbon atom is called as asymmetric carbon atom. What is it? Asymmetric carbon atom. Why? Because there is no, however you place it, you know it is a tetrahedral shape. That day I have shown you the tetrahedral shape, isn't it? The tetrahedral shape I have shown you. If any of the one of the group is having same, for example, if it is B, see, there comes the symmetric nature. So, when all the 4 valencies are satisfied by 4 different groups, underline, 4 different groups, then that carbon atom is called as an asymmetric carbon atom. So in some cases, in the questions, it is asked to find out whether the compound is having an asymmetric carbon atom. So, asymmetric carbon atom means in that carbon atom, all the 4 valencies are satisfied by 4 different groups. Okay, then the molecule is said to be asymmetric carbon atom, or you can call it as stereocenter. 2 words. Okay, this is only another name, asymmetric carbon atom or stereocenter. This carbon atom. Okay, so that process is called as, that carbon atom is called as an asymmetric carbon atom, or it is called as a stereocenter. Okay, then that comes, now how we will say the symmetry and asymmetry? You can say the asymmetry of molecule is responsible, you can say it in one word, which means if you ask who is responsible for this optical activity, then we can say the asymmetric carbon atom. So, the asymmetry of this molecule is responsible for the optical activity. Keep in mind, very, very important. So, what is necessary? So, if somebody asks you whether this compound is optically active, now what you should have to do? You should know whether the particular compound is having an asymmetric carbon atom. If it contains an asymmetric center or a stereo center, then that particular compound or molecule will show optical activity. Then one more thing you have to know in relation to this is, you know, symmetry, which means if I have a ball, or if I have this pen, which is circular, it will not circular in shape, then if I take this mirror image of this pen, that means if I keep a mirror in between, in here, its mirror image will be same as this, isn't it? Once again, if I have a sphere, you just imagine a sphere or this pen, which is round in shape, and if I take the mirror image means what? If I write this mirror image, see, if I have a sphere, if mirror image means you have to draw the dotted lines, which states that it is a mirror. Okay, so if you see the mirror image of this sphere or this circular thing, if mirror is placed, you can see the image of this is what? Exactly the same. For example, this is sphere, this is also exactly the sphere. Okay, now what you should do? Now you should make this mirror image to be this image is kept over this image, or the mirror image, you can just visualize it, this mirror image is kept on this image, which means what? Which means there is a symmetry in this, isn't it? There is no change in this. That means it is completely superimposable. There is no change. that this sphere is in same accordance with this sphere. That is called as superimposable image. What is it? Superimposable image. But if you say a right hand and a left hand, if you examine a right hand and a left hand, what is this? This is mine, it is a left hand. If I put a mirror here and if I look through that, I will get this, isn't it? Isn't it? So if it is a mirror here, this finger will be here. So that is exactly the right hand mirror image is the left hand. Correct? Now what happens? Now if you superimpose it, superimpose means put one upon another. See? Put one upon another. Then what happens? Is it superimposable? Is it? No. Why? Because this is not in accordance with this. So this finger is, the thumb finger is here. Isn't it? And the little finger is in with the thumb finger. So it is not superimposable. Which means that a term called as non-superimposable image. So the two hands are non-superimposable to each other. Now you know the difference between what is superimposable and what is non-superimposable. The best example is right hand and a left hand. That is, the right hand's mirror image is exactly the left hand. Now if you superimpose it, it is not imposing it exactly, because this is the little finger and this is the thumb. So it is not superimposed. So this is called as non-superimposable image. And a compound which has a non-superimposable image will show an optical isomerism or optical activity. See how it relates? First we said a compound shows optical isomerism only if that compound must contain an asymmetric carbon atom, isn't it? Asymmetric means all the carbon atom with all the 4 valencies are satisfied by 4 different groups. Then we said the molecule must be non-superimposable to each other. Now non-superimposable means, so now you tell me, when the molecule will be non-superimposable, tell me, when these two molecules will be superimposable, when is it? When that compound contains at least one asymmetric carbon atom, isn't it? So it relates like that. So a compound which contains an asymmetric carbon atom are non-superimposable to each other. Okay, that type of molecule is called as chiral molecule. See, that type of molecule is called as chiral molecule. And if it is superimposable, if the two images are superimposable to each other, then it is called as a chiral molecule. What is it? A chiral molecule. So, 2 more terminologies. So, I told you, so many terminologies we have to come through. So, you know what is a chiral and chiral. Chiral means the molecule which show this chiral property is called as chirality. Chirality means what? The two compounds with the mirror image of that a compound and its mirror image must be superimposable, non-superimposable, then it is called as a chiral molecule. And a chiral molecule, if it is superimposable, it is called as an achiral molecule. So, these are the examples of the chiral and achiral molecule. Okay. So, now you know what is molecular asymmetry and molecular symmetry. Symmetry means what? If either of one is B and B, then there will be a symmetry between that. However, you turn this compound, because it is an sp3 hybridization having a tetrahedral angle. So, in 3D projections, however you make it rotate, always there will be a symmetry, plane of symmetry will be there, or a center of symmetry will be there. Okay. So, that is why we say molecular symmetry and molecular asymmetry. So, now we will take an example just to illustrate how you will know, or how you know a compound is achiral or chiral, or will show optical activity. Okay. Now, just a simple example which is given in your textbook. It is said as, it is a Fisher projection graph or Fisher projection formula. That means you have a compound like C. Okay. Now OH, here there are HCH3 and CH3. Okay. That means I put this tetrahedral in side direction. Okay. Now you know last time we have studied all that. So this OH, then this is, now let me clarify this. Whether this carbon atom is chiral or achiral, or whether that carbon atom is asymmetric or symmetric. What will be your answer? Just see, all the 4 valencies must be satisfied by 4 different groups. See, this is OH, H, CH3 and CH3. There are 2 CH3 groups. So, is this carbon atom an asymmetric carbon atom? No. So, will this compound show optically active? No. So, that is how you say whether a compound will show optical isomerism. Okay. Or again, one more thing we have to find is, see here, this mirror image you see, mirror image. So, if this is A and the mirror image, in your book you can see dotted lines and edge lines. For example, if edge line is like this, if a bond is like this, solid wedge, that means it will project outwards. If a paper is there or if a board is there, if I say this is projected, this edge is projected outside the board. And if there is a dotted line, for example, if I say this is a dotted line, okay, that is studied in 11th, dotted line, which means that it is projected inside or inward. Okay. So here, here the mirror image will be what? Mirror image will be like this. See, H, CH3 and CH3. Okay. Now what you should do is, you can't, see very carefully listen, you can't superimpose this mirror image like this because it is not in the plane of paper, it is a 3D or 3D geometry, 3-dimensional geometry, tetrahedral. So, if we want the mirror image exactly what is this, you have to rotate it by 180 degree. It is the Fisher projection theory. This model was proposed by Fisher. Now if you rotate this mirror image by 180 degree, okay, 180 degree, you will get the same molecule. Okay, same molecule. Then you superimpose this, and if you find this is superimposable, then it is optically inactive compound. So if you rotate this, for example, if it is B, and if you rotate, you get C. Then C will be, then you have to relate this C and A. That means this compound, if you superimpose this, if it is superimposable, then you can say what? It is optically inactive. That is another method. Okay, many methods are there. First simple method is what? You just look for an asymmetric carbon atom. If it is an asymmetric carbon atom, it will show optical isomerism. Or you can have this Fisher projection formula, that is, you give that mirror image, you rotate it to 180 degree, you will get a product, then you superimpose that with the initial one. If it is superimposable, then it is optically inactive. If it is not superimposable, it is optically active. Okay? Okay. So this is optically inactive. We know because this carbon atom is a symmetric carbon atom. But if we have, instead of CH3, if we have C2H5, will this compound shows optically active nature or optical isomerism? Yes, definitely. Why? Because this carbon atom is optically active. Why? Sorry, this carbon atom is an asymmetric carbon atom, or this is a stereo center. Why? Because all the 4 valencies are satisfied by what? 4 different groups. One is C2H5, one is CH3, one is H, and other is OH. See, all the valencies, all the 4 valencies are satisfied by 4 different groups. So this shows optical isomerism. Now, if you look this Fisher projection, again what you will have this C2H5 here, the mirror image. But when you rotate this mirror image to 180 degree and make this last compound to be superimposable, then what happens? It is non-superimposable. Why? Because I will tell you, this will be OH and this will be CH3, this is C2H5 and this is HC. If I put this compound to this is the compound which this mirror image on rotating to 180, you will get this compound C. When this C compound is made to superimpose, then it is non-superimposable. Why? Because in the C2H5, here there is CH3, different. In CH3, it is C2H5. So, it is non-superimposable. So, that is how you you find out whether a molecule or a compound is superimposable or not, or optically active or not. Okay, just if you get away with this Fisher projection, you just see the simple method is what? To know whether a compound is optically active or no is to know whether it has a asymmetric carbon atom. That is the first and foremost thing. So that is about the asymmetric carbon atom and what is it? Fisher projection formula. Yes, Fisher projection formula to see whether a compound is optically active or not. So hope you understood this formula. Now, don't go into detail for this. You have just in your textbook, it has just explained like that only. Okay, it is like this. If you put it, for example, what happens if you put it 90 degree? 90 degree means it won't give the correct formula, correct projection of this same molecule. Okay, so that is why they put 180 degree. If you rotate this 180 degree, then only you will get the same molecule. Then you superimpose it to see whether it is optically active or optically inactive. Now you know a better idea regarding the stereochemistry, or you can call it as stereoisomers. You can call it as stereoisomers. Okay, because two molecules having two different geometry, you call it as stereoisomers. Okay, having same molecular formula. That is what isomerism stands for, isn't it? So, it is stereoisomers. Now, you have a pair of stereoisomers. Okay, and that too, if the two isomers are non-superimposable, listen, I am talking about two isomers, which means one will be the mirror image of the other, correct? Okay, then, if that mirror image, when you put it into the initial one, if it is non-superimposable, got it? Which means if two stereoisomers which are non-superimposable to its mirror image, then we can say such isomers are called as enantiomers. What is it? Enantiomers. So, what do you mean by enantiomers? Enantiomers means they are also stereoisomers. Now, what are stereoisomers? Isomers means carbon atom having four different groups are called isomers. The mirror image is also isomer. Correct. So, they are called as pair of isomers. So, for example, if I say carbon, then A, then B, then it is D and E. Suppose this is just visualize. See, if I can only draw in a two-dimensional plane like this, in the plane of paper. But this molecule, you have to visualize in what? You have to visualize in a 3D structure. Isn't it? So, in an sp3 hybridized tetrahedral shape, you have to like this. Tetrahedral shape, you have to visualize it. Okay. So, in this 3D structure, in a tetrahedral shape, if I say this is a isomer. Okay. Now, its mirror image is what? Its mirror image will be C, here it is B, here it is D and here it is A. Correct? Correct. So, this mirror image, so these are two stereoisomers. Am I right? Now, if these two stereoisomers are non-superimposable to each other, now what do you mean by that? Which means that I took this compound and keep up on this compound. Now what will happen? If this compound is taken and put it in this compound, what will happen? Where the B will come, the C will be there. Yes, point of symmetry is there. But see, other things, the B will be here. Instead of B, it will be B. Instead of B, it will be D. But the other thing remains same. That is okay. We need an asymmetric combinator, that is all. Isn't it? Like this. See, if you have like this, only thing is what? All the three are alike. Only thing, the last one is different. Likewise, in this case, what happens? This is when you superimpose this image, it is non-superimposable, which shows that these two are what? Stereoisomers, or you can call it as enantiomers, which is optically active compound. So, what are enantiomers? Enantiomers are stereoisomers which have non-superimposable mirror images. What is it? Value point is non-superimposable mirror images. Non-superimposable mirror images. See? So, this is called as enantiomers. So, you got it, the idea of what is enantiomer. That is, its mirror image. So, there are two stereoisomers. They are different in what? The mirror images which are non-superimposable. If you put one on the other, it won't be like same. So such type of stereoisomers which are having non-superimposable mirror images are called enantiomers. And let me tell you, these enantiomers there are two stereoisomers which you call it as enantiomers. These enantiomers have same physical properties. Same physical property. That means solubility, melting point, boiling point, refractive index, etc. same. But the only difference is, listen, the only difference in the enantiomers is optical rotation. That is, if this, you can't say this will rotate to right and this will rotate to left. That is up to that when they come across with that experiment, we will know according to the angle and the degree of rotation. So, if this rotates to right, definitely its enantiomer will rotate to left. That is the only difference between the enantiomers. Got the point? So, what are enantiomers? You have to study all this terminologies. Okay, that is why I put all the terminologies. Then we will go into detail for the SN1 and SN2 mechanism from the point of stereo aspect. Okay, from the stereochemical point of aspect, now we will see what is SN1 and SN2. But after all these terminologies are over. So now what is enantiomers? Enantiomers means non-superimposable mirror images which are two stereoisomers, or simply you can say two stereoisomers, or they are stereoisomers which their mirror images are non-superimposable. And they are having all the physical properties same almost, but the only difference is what? The degree of rotation. Now one, if it rotates to right, definitely the other will rotate to the left. So is it clear? Now we will say one more terminology, that is called as racemic mixture or racemic modification. Now what do you mean by a racemic mixture or a racemic modification? Okay, we will see what is it. Okay, a racemic modification or racemic mixture. Now imagine I have enantiomers, for example A and B. Okay, enantiomers are there. Or I will draw one example. I have, for example, the same I will draw A, B, D, E, and its enantiomer. What is it? A, B, E and D. These two are the enantiomers. Now you know that it only differs in the rotation, that is optical rotation. Now let us assume this is D, that is dextrorotatory, and this is levorotatory. And also you should know, if this has got an angle for, say, it rotates the PPL to an angle of 30 degree, for example, plus 30. Now this will be what? Minus 30. Because it is just opposite. It will rotate the PPL to left. Now, if I take, okay, I have two stereoisomers which I called as enantiomers. Now I take equal volumes or equimolar or equal volumes of these two isomers or enantiomers, or mixing equal volume of these enantiomers. For example, if I call it as A and B. Now if I mix A plus B in equal volume, that is very important, equal. Mixing up of these enantiomers in equal volume, what will happen to that mixture? If A is mixed with B, what will happen? The degree of rotation is different. Yes, we agree that. But if one is plus 30, the other is minus 30. So what will happen if you mix both? Plus and minus 30 cancel out, and it will have what? The value of optical rotation will be 0, isn't it? So it will have a 0, or it won't show any optical isomerism, or it will have a 0 optical rotation. And that type of mixtures are called as what? Racemic mixtures or racemic modifications. In two names we can say. What is it? Racemic mixtures or racemic modification. So what is racemic mixture or racemic modification? If two equal volumes of this stereoisomers, or you can have that word enantiomers. Okay, so equal volumes of enantiomers are mixed, you will get a compound or a mixture which is having 0 optical activity, because one gets nullified by the other. So that is called as a racemic mixture. So hope you understood what is racemic mixture. Okay, so these are all some of the terminologies of this stereochemical aspect or in stereochemistry. Okay. Then one more or two more to go. That is, so you know now what is racemic mixture. Okay, equimolar equal volumes of enantiomers. Okay, then when two enantiomers are mixed in equal proportion, whatever we can say, equimolar, equal volume, equal proportion, anything we can say. Okay, but it should be equal. Now that is racemic mixture. Now next is, you call it as retention. Okay, what do you mean by retention? What do you mean by retention? The word, the meaning of retention. Retention means what? A retention means, that means if a molecule has got a, for example, a definite geometry, or I will say a definite configuration. Now if I say configuration, you don't see that you will study in biomolecules. For example, if I say small d is for dextro and small l is for levo. But when we talk about configuration, we also come across with capital D and capital L. And this is nothing in connection with this rotation. This is entirely different, which we call it as configuration. And if you remembering, if you studied in the SN1, SN2, we said that in SN2 there is an inversion of configuration, isn't it? If you are remembering. There is an inversion of configuration in SN2, that is the umbrella which is pulling apart. Okay. Upside down umbrella, we said. So that is an inversion of configuration, and in SN1 we said there is no inversion of configuration. So that is inversion, that is configuration. That is different from this optical isomerism. So retention means, for example, I will say in example, then it will be very easy for you. Okay. That is, see, I have a molecule like A, the same molecules, A, B, C is there, D and E. Okay, this is a molecule. Now, if I made some reactions in this, okay, or if I want to add, for example, if there is a X group, okay, this is another group, this is another group, this is another group, this is X group. Now, if I want to substitute Y for X, for example, if I say Y minus, you will get C. I will get the compound like A, B, D and Y. See See the structure or symmetry of that, or the spatial arrangement of this. What is it? See, here this X is replaced by Y, no doubt. Okay, if it is not Y minus, since it is nucleophile, I just wrote it like that. So if this X is replaced by Y, but see the position, is there any change in the position or bond or in symmetry or anything? Is there any change? There is now no change. Instead, what? Except this X is replaced by Y. All of there is, if I want to say like the bond is not broken, if I want to say, but in reality it will break and another will come in the same position. But still, you can say the bonds are also similar in position. The only thing is the X is replaced by Y. That means the configuration of that molecule is retained. It is not changed. So that is the meaning of retention. Or here we call this as the retention of configuration. There is a defined definition in the textbook. That is, it is said as the preservation of integrity of spatial arrangement. It is nothing. It is nothing. It says that only a substitution takes place and all the bonds are being intact. There is nothing, it is removed. Only the X is replaced by Y. The symmetry of the molecule is not changed. The position of the bonds are not changed, which means that the configuration is not changed. That is why, or the configuration of that molecule is retained. So that is called as a retention of configuration. So that is why in your book it is given as the preservation of the integrity. It is preserved. That is, this bond or all this, the spatial arrangement is preserved. That is, in the book it is said that the preservation of integrity of the spatial arrangement of bond to an asymmetric carbon during a chemical reaction, that is called as what? Retention of configuration, which simply says that there is no change in configuration. That means this spatial arrangement, that integrity of that, integrity you know, right? Integrity. So that integrity is preserved. This spatial arrangement, that integrity is preserved. There is no change in configuration. That is called as what? That is called as retention of configuration. Only this Y, this X is replaced by Y without breaking up of the bonds, if you want to say. Okay, that is called as retention of configuration. Correct? Or if I can say, if you want an example, if you want a real example, if I say this is OH, this is CH3, this is C2H5 and this is H. Okay, now if I want to replace this OH by Cl minus, what will happen? All other bond remains the same except fluorine. See, even the COH bonds are same, the angles are same, everything is same. But only the the OH is replaced by Cl. All other things are preserved. All its integrity is preserved. Okay, so that is called as retention of configuration. There is no change in the configuration. Whereas in SN2 we saw there is an inversion of configuration, because if the OH minus is in this position and if the nucleophile is coming in the opposite direction, then it will attach like this and the product will be the reverse. Sorry, the nucleophile will be reversed. So that's why there is an inversion of configuration is there. So now you are clear with the retention of configuration. Okay. So there is no change in the bond. There is only a removal of something and putting back with another thing. That's all. All other bonds, everything is kept intact. Okay. There is no change in the configuration. Clear? And now the last is called as inversion of configuration. And you know what is inversion of configuration? You have seen in SN2 mechanism. What is it? What is inversion of configuration? Again, if I draw COH CH3 and C2H5. What will be the inversion of configuration? The nucleophile is coming in this direction, isn't it? Because to avoid the steric effect. Then what will be the formula? It will be H, then CH3, C2H5. Our reactant was the OH, the nucleophile was on the right hand side, but in the product it will be on the opposite side. So the configuration is reversed, isn't it? The configuration is reversed. So that is called as inversion of configuration. This we have studied very detailed in SN2 mechanism. So that is inversion of configuration. So what two types of configuration we studied? One is retention of configuration, where there is no change. The integrity of the spatial arrangement is preserved. Okay, so that is retention, and inversion means there is exactly a change in the configuration. If one is right, then the other is left. So this is, and then we say one more thing. What do you mean by, we talked about racemic mixture, isn't it? That means what? When equal proportions of these enantiomers are mixed, then you will get a mixture which is called as racemic mixture. Now we will see how you make racemic mixture. Okay, and that process is called as racemization. What is it? The process of obtaining racemic mixture from enantiomers, or converting an enantiomer to a racemic mixture is called as racemization. For example, see, if you have a compound, say is COH, CH3, H and CH3. If this is X, okay, this is a compound. This is a compound. Now, what happens if inversion of configuration happens? Listen, what happens when inversion of configuration happens? We will get the product as OH, H, retention. Okay, first we will write the retention. So, only the X is replaced by Y. Okay, this is when only what happens? Retention happens. Okay, so you will get a compound A. Now, here what will happen if inversion happens? Inversion happens. What happens? We will get the compound COH. Here it will be Y, then H, then here it is CH3. Correct? Now you will get a compound B. So, if you have a compound having an asymmetric carbon atom, if retention happens, you will get only A, because it is retention, the same bond is retaining, the configuration is retaining, okay, same relative configuration. Now here what happens? Inversion happens, because this here X is on the left hand side, here it is on the right hand side, so inversion happens. Now, we can say this A and B are enantiomers, isn't it? This is the mirror image of this. Now, if A and B 50-50 ratio, if you mix in equal proportion, you will get what? AB, which is called as a racemic mixture, which is optically inactive, and that process is called as racemization. And racemization we will put like DL or plus minus like this. Instead of plus and minus, racemization means what? Both together, plus and minus or DL. So that is about the terminologies in stereochemistry or stereochemical aspects of nucleophilic substitution. Now, considering all these aspects, we will look forward to compounds which are optically active. What will be the SN1 and SN2 reaction, or what will be the product of SN1 and SN2 reaction. So that we will see in the next session. So till now, please read the book. Any doubt, give me a call. We will do it. Okay, thank you.